Aerial Robotics Competition. We're the first Aerial Robotics team on the Norwegian and as far as we're concerned, we're also the first team from not only Norway but also from the whole of Scandinavia to compete in the IARC, which is pretty cool. Okay, so we started out last year as 6 guys who wanted to create an environment around aerial robotics at NTNU with the IARC as a common year goal. And we quickly grew to about 16 members, with several of our members writing their master's theses on the difficulties involved in Mission 7A. So we've divided our approach to Mission 7A into 3 key areas, starting with perception, which is responsible for gathering data from all our cameras and sensors, and to provide the drone with its position in the grid, as well as the position and orientation of all the ground targets, and of course, all the moving afterwards. Strategy uses this information gathered by and provided by perception to plan a sequence of waypoints to successfully interact with all these ground targets in a strategic manner to solve the objective in time. And lastly, control uses this strategy to actually execute this plan while avoiding all the obstacles on its way. When we started out last year, we built a cheap drone from off-the-shelf components to be able to start flying early. We just learn how to handle the drone and to sort of test out different sensors and cameras and solutions early on. But we soon realized that in order to fit all the sensors and cameras where we wanted, we had to build our own drone. And thus, Drone 2.0 was born. Our drone has a custom carbon fiber frame and carbon fiber arms, rather lightweight but durable structure. And the joints between the carbon fiber arms and the frame, and between the arms and the motors, are made of 3D printed cheap plastic parts with planned yielding in place, so that in the event of a crash, which never happens obviously, the joints break, ensuring minimal damage to the drone. And they are quick, easy, and cheap to replace in case of a crash. Additionally, we use the Pixel flight controller as our PX4 flight stack for our low-level stabilization and flying. And for our onboard computing, we use the Intel NUC to run things like obstacle avoidance and our visualization software. And we also have a more powerful ground station that we tether it through with Wi-Fi that runs more demanding software like our target detection software. Continuing on the payload, the Pixel provides us with an inertial navigation system, including an accelerometer and magnetometer and gyroscope. And we have a downward-facing LiDAR light rangefinder for height measurement, as well as 4 side-facing Logitech C920 web cameras that we use to detect the 4 unique corners of the grid arena. We also have a downward-facing fisheye camera that we use to detect the grid arena, as well as the ground targets. And lastly, we have an OcuView planar scanning LiDAR on top that we use to detect the obstacle robots. Using the data feed from downward-facing fisheye cameras, combined with our last measured pose and the height from the LiDAR light, we can determine the drone's position in the grid and use this to tell it exactly where to go to interact with the robots. And what you're looking at here is just this grid localization algorithm drawing back where it thinks the grid is, which you can see is pretty accurate. When it comes to strategy, we had 2 of our team members writing their master's theses on the strategy of interaction in Mission 7A, which they modeled mathematically and formulated as an optimization problem called the time-dependent orienteering problem with time windows with ant colony optimization, which works by planning a sequence of waypoints to maximize the expected reward And the reward is calculated using metrics such as time of arrival, likelihood of successful interaction, and the target's distance to the edge of the arena, or to an obstacle, or to another target robot. And to test this algorithm and compare it to other algorithms, we developed simulations of Mission 7A to be able to gather a large sample size of data to actually test out these different algorithms. And what we found is that a greedy algorithm, which just selects the target robot closest to the green line and just focuses on getting this across, actually performs pretty well, especially in the early stages of the simulation where there are a lot of ground robots in the arena. And the greedy algorithm actually manages to get all 7 ground robots over the green line in about just over 6 minutes, which is the minimum requirements of solving the mission. But in our simulations, it never managed to get all 10 ground robots over the green line in under 10 minutes, and thus not giving us the maximum possible score. But the ACO algorithm actually surpasses the greedy algorithm at around 7 ground robots and manages to get all 10 ground robots over the green line in just around 8 minutes on average in our simulations. What you're looking at here is an illustration of a key difference between the greedy algorithm and our ACO algorithm. This is a snapshot from our simulations where you see the grid arena here, and blue circles are the obstacle robots, and the yellow circles are the ground targets, and our drawing is the huge circle with the cross in the middle. So in step 1 up here, you will see there are 2 ground robots very close to the green line, and the greedy algorithm would just focus on these 2 in the beginning, but our ACO algorithm knows that these 2 will cross the green line unattended, so it will plan a new path involving the 2 ground robots around the middle of the arena. But as it executes this plan in step 2, you can notice the ground robot to the left here crossing into we call it dangerous area, where it might risk exiting the arena on the wrong side. And our algorithm notices this and can thus plan a new path that executes in step 3 and step 4 to avoid losing this ground robot and thus avoiding a negative score. And we know these are just simulations, and we're making a bunch of different assumptions, like the amount of time it takes to actually interact with the ground robot, as well as having complete information of all the ground targets. So, and actually implementing this, we expect to, of course, get different results, but nevertheless, these results are pretty interesting. That we have an algorithm that actually performs better than just a greedy algorithm. I'd like to just summarize with what we will be demonstrating this year and what we're setting up for next year. So this year we have a positioning locked down pretty good. It works really well, and we'd like to demonstrate that our drone knows where it is and we can tell it to go wherever in the arena, as well as target detection and obstacle avoidance. And we've developed this pretty looking GUI that we will use to demonstrate our systems. And for next year, we'd like to really lock down target interaction, not just detection, and as well as strategy implementation, starting off with the greedy algorithm and then moving over to the ACO algorithm that I mentioned earlier. Yeah, that's it for me. Thank you for your attention. Are there any questions?
So you'll be flying around?
Well, we haven't, autonomous takeoff is not working as we'd like, so we'll have to take off manually. But once we're in the air, we will be able to fly autonomously. Yes. Any other questions?
Did I hear you that in your game strategy that you made the assumption that you have perfect knowledge of all the ground robot position?
I think we've run different simulations. There are some simulations that assume complete information, but actually it doesn't work when there are a couple of robots that are like off like we don't know what everything about this.
I was just wondering if the plot that you showed is
I think
with or without
yeah,
perfect knowledge.
I have to check this thesis later, but I think that assumes complete information. Yes. Anyone else? All right, thank you.